New topic for today's session is called computer security or security. If we already know that we will not talk about physical security and other related things. And before we go in more details, we need to answer the question what is secure. And in general, something is considered secure if it is either private and secret from outside and others, so you can hide some secrets from everybody else, either when you store or hold something or when you transmit some knowledge and information to somebody else. It is also considered secure if it is harmless or safe for users, so it doesn't hurt you. And one of ways how it can hurt you if it just breaks when you are using it. And then, of course, it should be strong enough and robust and resilient enough that if somebody tries to break it, it can stand these malicious attacks. So you can store your data properly, you can transmit the data properly, so they are resilient enough against some potential harm from malicious users. But as you probably know, in internet and in this digital space, there are quite a lot of malicious users who try to attack something or somebody, border criminals, border teenagers, criminals, organized crime organizations, rogue state departments, etc. So why do they do it? Border teenagers do it for fun or fame. Usually criminals and angry employees and states does it for profit or for revenge or whatever. And the important thing here is that you should remember that when you are using internet, you are not at home. You are in public space like on street. And if overall state of street rules is poorly managed, like people are not loyal to government is not loyal to people, and policemen are corrupt, etc., then of course street rules are quite harsh. And similarly it's about internet. So if you are somewhere in some dusty corners and places of internet where these rules are not well established and well managed, of course you may be hurt in terms of your lost data, lost money, lost image or other things. And many of these malicious attacks are done automatically using malicious programs. We will review how these programs are breaking into not so secure systems later, but you should already know that there are different kind of viruses, worms, Trojan horses, and just inconveniences like distributed denial of service attacks and spams, email spams like different kind of stupid advertisements, etc. And so how do you risk with these not enough secure information systems? Somebody may use your identity, somebody may break into your unpatched system because there are no known vulnerabilities in your system. You may, and because of that, you may lose some money, you may lose some private data, etc. And why such attacks happen? Firstly, because software is very complicated and nobody understands everything from the deepest hardware level to the highest application level, how exactly these things work. So if we are caring only about hardware, we need to trust that only trustable software will be run on this hardware. If we are using software on this hardware, we may believe that the hardware is not malicious, but there are not 100% guarantees that you can always check everything from the lowest hardware level till to the application level, that everything is trustable and everything works as it is expected to work. And particularly about different kind of software and computers in general, this is drawback of this universal computer called one name and architecture, where there is not a distinction between data, which represents instructions for execution, and data which represents some kind of handled data inside this program. Of course, when we will talk in more details, even though architecture allows to mix these two things together, like data which are executed as a program and data which represents actual data to store different values, there are built-in security features. For example, in most of programs do not allow to write into that space of program which is marked for execution. So even though hardware allows you to load everything and try to execute as a program, in practice there are two different parts of loaded data. One data says it is read-only for execution, another is read-write for reading, writing, and not for execution. But because there may be bugs inside of all this architecture, how software and hardware works, there are still different kind of problems there. So, and there are unsafe programming languages used still, where you can make different kind of bugs, where you do not distinguish between these two different parts of memory. And so everything is just too complicated, and these who write software do not go in details about hardware. These who develop hardware do not go into details of software. So therefore there are many places where these bugs may be hiding. And also, problem is that nobody needs 100% secure systems, because in most of the times good enough security is good enough, and good enough security is always much cheaper than 100% security. So every time you write some application, you usually just try to get it working for non-malicious proper users, and you fix different kind of security bugs only as far as it is economically possible. And of course, other thing is that because of all this complexity, the weakest place is always human factor. So even though you have almost perfect computer systems, there still may be malicious users and developers who actually try to break these systems. And now about different kind of aspects of security. First thing is about this secrecy and privacy. That secure means that you can hide something from eavesdropping from everybody else if you want to hide something. And important foundation for hiding some data is cryptography, or encryption and decryption of data, either when you are holding and storing them or when you are transmitting them from place to place. And so most important goal for cryptography is to ensure that you can ensure confidentiality. That means something which is intended to be private or secret is actually private and secret, so even though somebody may get these data are encrypted, so even holding this encrypted data do not help them much because they can't get actual information because they are unable to decrypt them. Another part is integrity. If you send some data, even though these data are intended to be public, you may need to authenticate these data, that these data are sent from you, not from somebody else. So here talk is about a thing called digital signatures and adding like a digital stamp on your data that this is official document coming from this particular source. And internet in general is a hostile place because you cannot distinguish between good users and bad users in internet. So this means that in times of cryptography you have to assume that internet is an secure place, so you need to have different kind of controls and approaches how you can use internet, send, receive data and store this data somewhere, even knowing that there are some malicious bad actors using the same data transmission networks, the same devices as you. And there are different subparts of cryptography, but one of things what cryptography is not is hiding something just in a way that nobody else knows how you actually have hidden something, like steganography is covered writing. You hide something, some data in some other data, as presumably or assumably that nobody knows how exactly you are hiding data inside data. For example, you may put hidden pictures inside pictures just by changing last bit from 1 to 0 or 0 to 1. So everybody who will look at picture will not see any color differences. But if you know that you need to care only about this last bit representing particular pixel on this picture, then you can read it and use it. But problem with steganography is that it is not secure enough because it is hiding by ignorance. So if somebody is ignorant that he or she needs to search some data inside data, then it may be safe. But if they actually try seeking it and analyze this data, then it is actually not encryption, it is just stashing or hiding something, like if you stash something behind sofa. So if nobody cares to look what is under or behind sofa, then it is safe enough. But if somebody actively seeks for different kind of places, of course, finding something behind or under sofa is quite easy. And then there are actual hiding data or cryptography, which uses more proper ways that even though you know that there are some information in this encrypted data, without knowing particular key which is used to lock this data, you can't unlock it. So it would be something like this. Putting something behind sofa is steganography. Putting something in secure safe and locking it with key is cryptography. So even though everybody sees this safe, they cannot break into it without proper key. And then there is science called cryptanalysis, which analyzes different kind of approaches, how you can put this data into safe, that only with proper key this data can be unlocked. And history of cryptography is very old, so it was invented together with writing. So information was king and information was oil even before oil was discovered. And so there was always need to send information from place to place in such ways that nobody in between can read this information. And initially all these cryptographical methods were used in such ways that everybody can encrypt and decrypt it just using pencil and paper. But of course, when computers were widely used enough, there are hundreds of different cryptography methods where you use computers. And what is basic terminology? So when we will talk about older school methods, for illustration we will use text because it's easier to understand and illustrate. So then you have this plain text or original message which is not encrypted. When you encrypt it, you get it as a ciphertext. Then you use different kind of keys, which is this private secret data which are used to unlock or decipher this ciphertext. And when you encrypt it, you make plain text into ciphertext, and when you decrypt it, you make ciphertext into plain text back. And cipher is particular encryption algorithm which is used for encryption or decryption. An important part is that steganography is like substitution. It is not encryption because you can hide data only for those who do not care to search for this data and information. And what is also not encryption is when you rewrite some information in different encoding form. For example, if you have plain text apple and you rewrite these characters as a ASCII decimal codes here, it is not encryption. This is hidden secret only for these who don't know anything about ASCII codes, who don't know that this looks very likely as a sequence of ASCII codes written in decimal number system. Similarly, if you translate apple shown as the characters into ASCII codes using hexadecimal numbers, again, it is not encryption, it is just encoding to something else. Or if you write it in base 64, again, it is not encryption, it is just different kind of encoding. And everybody who has knowledge about base 64 and about texts knows what it is. Similarly, if you rewrite in binary code, similarly if you rewrite it in Morse code. And also, it is not encryption if you translate it from like English to some different language. Of course, it may be abracadabra for those who do not know this particular language, but if they know, if they do some analysis, then of course rewriting it to ABOS or YAWLOC or whatever, it is not encryption. It may be used as a steganography, but just hiding information behind something, but it is not real encryption because it can be very easily broken. And one of the first ciphers for encryption was invented in ancient Rome, called Caesar's cipher. It is to replace one character with some other character. And for example, here is how these are called, text where all Latin letters are shown, and then when you substitute them, then you get some kind of abracadabra. But such encryption is very weak because you do not lose metadata or data about statistics of particular language used. For example, if we do text analysis, so here is some text in English, and here is content, but what we can do is we can very simply analyze it. So here is Bash script, which does following. First, replaces capital Latin and Latvian letters to lowercase letters, then replaces every space between letters as a new line, then translates some specific marks to something else, then sort everything, count how many unique letters there are, and then sort everything by number. And here we see what is statistics about English text. So the most common character is space, then E, T, O, A, N, blah blah blah. Similarly, if we use some Latvian text, and here is in Latvian Mērnieku laiki, we do some statistical analysis, and here we see this analysis for Latvian language, and as you see, it is different for Latvian and different for English. And if you just substitute something, for example, you substitute letters A, B, C, D with shifted letters B, C, D, E, E, F. So you get something like this. But when you do statistical analysis, you will see that what was letter A previously here in, let's say, Latvian or English, now it will be different letter. So if you do simple substitution and encryption, then it is very weak because it still holds all these properties about plain text by statistical analysis. So, and here is graph showing what is distribution of different letters in English, and here is what is distribution of letters in Latvian. So it is not equally distributed, and you can always analyze what is actual letter. So similarly, in ancient times they used another cipher which is also quite weak because it preserves statistical properties of the text. Is you write text into square with cells and rows here, and it actually may be not square but something else. So you write something here and then you encrypt it, you read it for example, in this order, and then that order, and then that order. So only secret key here is how many rows and how many columns you are using. But again, in such encryption, this encrypted text ciphertext preserves all these statistical properties of plain text, and therefore it's quite easy to understand. You just need to try out different number of rows and columns and check in which particular order these are done, and of course using computers such permutations are quite easy to do. So one of more proper approaches to encrypt something is to shift letter in circle. In Latin alphabet there are 26 letters, so somewhere here is half of them. And when you say that you shift something like letter A with letter B, which means you add number, if it's letter A you consider 1 or 0, let's consider it 1, then B is 1, so your final letter is like B. And if you shift it by C, then A becomes C, but if you have something like C and shift it by C, it's like 3 plus 3 is letter 6, which is I do not know. So you shift these letters, and then when you get from Z and add some letter to Z, like B, you shift it forward again. And when you decrypt it, you need to subtract these letters here, which you assign just as some kind of numbers, to get this text back. And what is important about such approach is that it is secure if your key is secure. So if you use the same repeating key, just A, then all your these letters are shifted by the same amount forward in this circle of letters. And when you try to deshift it back, for example with this key and this, you get this output back again. But of course your key may be much different. And of course. And then, because if this string which are using to add and subtract these letters is random enough, then all these properties about text, how widely were distributed these characters, are deleted, diluted, because for each particular letter you shift it randomly, and so then breaking it becomes much harder, and particularly and so this is good enough cipher. Only problem is that you need to send this key which you have used to encrypt and decrypt this text secretly. So that's a problem. And how does it works in computer? Usually you do not use like circles of letters, because when you encrypt different kind of data, plain text, formatted text, images, etc. So these are not just letters. So you use similar approach, but you usually use exclusive OR Boolean operation unexclusive OR means following, that here is your line value, and here is your key value, and here is output. Let's start with both zeros. So output for XOR is that it shows 0 if these are equal and shows 1 if these are different. And good thing about XOR is following, that you have this plain text and you add XOR once, you get this one out, and when you do second one time, you get plain text back. So with one XOR you shift these bits to something else, applying the same XOR again, you get the primary initial result back. And so here it is shown how it works. So if you have plain text in binary, just zeros and ones following, and you encrypt it with XOR key like this one, so every time these digits are the same, you get 0. If these are different, you get 1. So here it is your encrypted ciphertext or cipher bits, and then you decrypt it with the same key again, and you get plain text back again. And so that's how computers work. But a problem here is that in most of cases your encryption key is much shorter than data what you want to encrypt, because if key needs to be as long as actual encrypted data, then of course you have a problem, because you need to send quite a lot of data around securely for encryption and decryption. So therefore what is actually happening is that there are different kind of approaches, that if you have a long string of bits for data and you use much shorter key, you somehow repeat this key in secure way, that you can reuse this key as many times as you need to encrypt entire data here. And you can't just use repeatedly this XOR operation as Boolean operation, because then again, if you will do statistical analysis, you will see irregularities, that if, for example, this key is, let's say, 8 bits long, so there are reoccurring things that sum of bits, like 8-bit regularities, occur much more frequently than 12 bits more and more bits. So that means that if you reapply just XOR many times with this key, you again can do statistical analysis for encrypted text to see what this encryption key is. And when you know encryption key, of course you apply it, and then you can decrypt the data very easily. Therefore, here what is important is that you do different kind of additional operations to dilute, izšķīdināt, these properties of particularly used key in much longer binary strings. And in general, what do you do is you do first shifts. For example, if your key is only as long, you add key with some bit shift here. Then you use regroupings and reverse inside like block. Some bits are shifted forward, some bits are shifted backward, and then you do it with much larger blocks, like this large block, and this goes here, this goes here. this goes here, this goes here. And then you use these XOR operations, so you need to dilute these regularities appearing in particular bits for key as much as possible in larger and larger blocks of data, that there are no, that if somebody uses statistical analysis, it can't see any good regularities for particular distribution of particular lengths of bits for zeros and ones, etc. And the most widely used standard, how you do this, is called Advanced Encryption Standard. So it is, algorithm is open source to everybody, so everybody knows how this algorithm works. Before that was used this algorithm. It has also hardware support for most of personal computers and other hardware, so all these operations with bits, what I told you, are done in hardware, so it works much faster than done in software. And you can use as short key as you like, but shortest thing what it uses for blocks is either 128 bits, 122 bits or 256 bits. And currently there is no any vulnerability for this encryption find out, so this is as secure as your private keys are secure and as long your private keys are, because if you have very short messages encrypted with short keys, only known method to break this advanced encryption algorithm is just brute force attack. That means do all possible combinations for used key, starting with 0, then 01, then 001 with different lengths and different values until you just break it. And if only possible way to break such encryption is brute force attack, it is considered secure, because for any large enough an amount of data, time you need to break is very big. So let's say millions of years or billions of years. But then if you have very large amounts of data, you need to be careful, because for these block encryption modes, if you encrypt only one single block independently, you still may see different kind of patterns emerging. And here this advanced encryption standard is used to encrypt something in block mode for this image, and how much it could be, let's say few bytes as a block. But because you get the same output encrypting for the same input all the time, for example, if here is white background, you always will get some kind of grayish pattern here as the encrypted text. So again, you can do statistical analysis to understand what is exactly hidden here, because if you encrypt these blocks independently, the same block as an input will give you the same block as an output. So if they are the same input, like the same color all the time, even though it is changed, you still see regularities and patterns there. And therefore what is actually needed here, when you encrypt long messages, you use output of previous block as additional input for next block. And then it adds additional randomness into these things, because now each particular block is dependent not only from actual input, but also from output of the previous block. So then it is much secure. You see only some random noise as a pixels here. Only problem is that if you lose one single bit somewhere here in the picture, you can't decrypt anything else after this single bit is changed, because everything else after that will be broken. So that means you need to add additional layers of redundancy to be sure that these data are sent with precision to single bit, because otherwise everything after one broken bit here will be wrong because of this dependency of next blocks of previous blocks. So that's about encryption. So other thing is about authenticity, or how you can declare that something is not broken, that it is what it intended to be in the first place. And here different kind of hash functions plays a role. What is hash function? Hash function is a function which maps any arbitrary input into, like, usually it is like pseudo random number, but into much simplified output. So in theory, if you look on probability theory, there are almost infinite amount of possibilities what kind of data you can funnel into hash function. And hash function usually is shown as a two-dimensional funnel, so large input and small output. And for any infinitely large amount here, it always provides fixed length output. And if you look in binary, it's just binary number. If you look on hexadecimal, it's hexadecimal number. So, because output is much smaller than potential input, there may always be some cases when you have so-called collisions. What is collision? Collision means that you provide different input to this hash function, but it has the same output. So collisions are bad things, but good thing is that you can describe all the bits inside particular input with just one single number, and if just one single bit is changed to this input, then output is completely different. So, and because of that, you can use hash functions like signatures for your data. That means if you always get the same value for particular hash function, then you know that every single bit, even in megabytes and gigabytes of data, is proper, because if just one single bit would be changed, then entire hash function would be changed. And similarly to encryption, hash functions use the same approaches to get value. So if you have very long strings of bits, these bits are somehow grouped together, then these groups are added using XOR, then these bits are shifted, one bit left and then next bit here or in other direction, then these bits are swapped in places inside smaller block, then large blocks are swapped in places until you just get one group of these bits. And if you will look for one how this particular bit is influenced by input, and we look from algorithm, you will see that this bit was traveling from here to here, then it was shifted here, then shift here, then it was added here, then it was added here, and then it was added here. But similarly, some completely different bit did completely different paths. And so for hash functions there are these two things, dilution and confusion. So what is dilution? Dilution means that one single bit here, either 0 or 1, at the end makes that every single bit in output will change with probability of 50-50% here. So just one single bit changed here for hash function output will change bit to different with probability 50-50 here. Next bit will also be influenced by probability 50-50 here. So one single bit is diluted into entire output of this hash function, and it's for any single bit here. So it is diluted. And confusion is in opposite end. So if you look one single bit here in output, and you check how exactly this particular output bit was influenced, you see that it was 50-50% chance that it output bit was influenced by this single input bit, 50-50% chance that output was influenced by this single bit here, etc. So now it is confused from one single bit here to entire input data here. Because of this confusion, going back from particular hash sum to initial amount of data, if you do this actual analysis, is very hard. So in general, that means you need to do brute force attack. But hash functions are not encryptions, because for any single input, you always will have one single output. So relation is 1-to-1. The relation between probabilities value of which bit will have be changing is many to many, but for one particular single input there is always one particular single output. So if you look on this probability space, you have this very large probabilities of different inputs and much smaller space of outputs, because you always have just single number here, but one value here is always related to one value here. And of course, if you have collisions, you may have the same value here, but more than one here. But if you ignore collisions, it is 1-to-1. And because of that, hash functions can't be used as an encryption. For example, if we say echo apple and say create hash function using MD5 sum for it, we get following number in hexadecimal. And going back from this number to apple is very hard, except if you save it as a table. And there is internet is full of these values that everybody knows who is not lazy, that this particular number in hexadecimal is from this particular output. Similarly, if you use different hash sum, and you search for it, you see that it is reverse value for apple again using SHA-1 algorithm. And if you use something like SHA, SHA-512 sum, so this hash is much longer, so probability for collisions is much lower. But we still know that the hash here is for word apple. But hash functions may be used for encryption using additional random input for this apple. And the simple way would be something like this. And in proper salting, this salt again is diluted in entire additional string, something like we can do like this. So there is some random key here added to apple, but because probability that somebody will use salt and apple together here is much lower, if I search for this particular hash sum, I see that there is no already calculated correct answer. And that's how you use hashes to encrypt some data. For example, for passwords, to know that some user is sending proper password, One of trivial things is that you store your password as a plain text here, and if you send this password and you check this is the same string, then this user knows his password. But problem is that if you store it in a such way, then everybody who is not lazy, who break into system, may read all these used passwords. And therefore, instead of plain text password, you hash it too. But just simple caching would not be enough because of these stored tables of already guessed unknown values. But if you have like password diluted with secret key, and then you make hash for it, and then you say that secret key is following, and hash for password and secret key is following, then nobody knows how to decrypt this password again, because there is no known solution for secret key and password used together. And how does it look in Unix-like systems? This is configuration file where passwords for user are stored. And it is base 64 encoded. Here it says what kind of hashing function is used, and I think 6 is that is SHA-512, because if I look on length of this hash here, it is quite long. And this is salt for this password. So I got this particular value of this hash function with my password, which only I know, together with this random string. And this random string is not like concatenated like two strings, like this value and password. But again, bits of this salt string are mixed up in different ways to this password string, and then this hash was calculated. And so then nobody knows what actual password is, but if I give my actual password and it is mixed with this particular key, or this key in this case is called salt, then I got this particular value for this hash, and if this hash is the same, so this means I have given proper password to the system. And what are well-known hash functions? MD5, it is quick and fast, but you shouldn't use it because there are known algorithms how to get collisions for it. And if you use MD5 as a digital signature for some data, that means somebody can try to make false data with the same digital signature. Then there is SHA-1, SHA-2 and SHA-3. And SHA-3 is the most advanced and which has the longest output as a number for it. For example, MD5 is just 128 bits, SHA-1 is 160 bits, and SHA-3 is still to 512 bits. And all these are good enough. For SHA-1, in theory, there is a way how to get collisions, so that means it can create digital signature for the same digital signature for modified input data. But it is not easy to do, so in most of cases it is good enough. SHA-1, by the way, is used as a signing algorithm or hashing algorithm for Git version control system. But these other are no known vulnerabilities. So that's about hashing. And now about public and private key encryption. So far what I showed you here is that problem, particularly for encryption, is that you have to send this key privately and securely to the other end of receiver, because the same key is used for encryption and decryption. And until 1970s, it was thought that only way how to encrypt something and decrypt is just using the same key. But later it was discovered that there are mathematical approaches that you can use different key to encrypt some data and different key to decrypt this data. And these are called public-private key encryption or public-private key ciphers. And how do they work? So in general, they work in a following way. One is RSA, which is most widely used for today, and it uses this property that first you use limited number space. For example, you decide that all your numbers will be from 0 till to infinity, but it will be from 0, I do not know, till to 128. And when you add +1 to 108, then you get 1 here again. And if you add +3, you get, so all your numbers are not infinite, but finite cycle. And of course, for good enough security, these should be big enough. And length for this number, not how many numbers are, but length of these numbers for RSA usually is 2k till to 4k in binary digits. So this means minimum is approximately 2 kilobits of zeros in this space, and maximum number is approximately 2 or 4 kilobits of ones here. And then from this limited space you pick up some particular numbers, which are prime numbers. And then if you use such arithmetic that your biggest number for calculation is just number n, and you pick up two different numbers in such way that given number in in power of e and then in power of d, and number in power m power of d and number of e, of course, e is the same number. And then you pick up that one of these powers will be one key and another will be other key in general. But when you use them, because of this cycle of different operations, using this or that particular numbers for these operations always will give you the same result. And then you use one of group of these numbers as your private key, which is secured, stored safely in particular place. But other is called this public key, which you give to everybody. And property of these keys are following: that if you have some plain text and then you encrypt it with your private key, then you can't apply the private key again to decrypt it. You need to apply other related key to decrypt it and other way. And a more modern and more efficient algorithm is called elliptic curves. So elliptic curve are these curves which describes following situation, that properties between numbers on this curve in general are following: that y is here and x is here, y squared is x cubed plus ax plus b, and depending on parameters, these curves may be different, but always this curve should be that it has curving here around this table, around this area. And then you pick up integer numbers as whole numbers on this plane. So if you use it as a infinite function, there are of course infinitely many different numbers, but there are always a limited amount of numbers which actually fits as a precise whole number on this particular curve. And then similarly you use the set of these particular numbers of this curve as your so-called finite field numbers. And then again, using different kind of approaches, you may use one set of numbers and other set of numbers as two different keys to do these calculations. So in general, in elliptic curves, what you do something like this bit shifting from letters. For example, if you have letter A here and you shift it by letter A again, so you add like 1 to 1 and it goes to this number with precise integer coordinates. And when you add it again, it goes here, then here, 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 and then into loop. Then if you add B, again you add a little bit more and it goes into cycle again. So this algorithm is much faster, but it is unfortunately not so widely used yet. But in general, for example, if you do public key exchange to create sessions, etc., so elliptic curve algorithm is a better one. And so how these signatures work? First you create your own set of public and private key, which will pick up particular numbers either for this RSA algorithm or particular numbers for particular elliptic curve on this elliptical curves algorithm. And then these two sets of these numbers, one of set will be your private key, another set will be public key. And for example, if you want to sign something, because particularly RSA algorithm is very slow, you do not sign entire document because it takes, for example, if you have megabytes or gigabytes of data, it will take maybe many minutes, maybe hours, depending on how fast your computer is. What you do first is, for this large input, you first calculate hash function for it. Because the hashing works much faster, because it has hardware support, and because these are just bit shift, bit change operations which computers do very quickly. And then you encrypt this hash function with your private key. So you have like hello Bob as an input, then you create hash for it, and then you encrypt this hash with your private key, and then somebody gets this hello Bob and then can verify. How do they verify? They calculate hash function for it, get this hash function, actual hash function for this data, and then they encrypt or decrypt with your public key. And if this particular value, what was given together with actual data, is the same as hash function and the decrypted value for this one, then you know that this particular document is authentic, because this particular content could be signed only with from this user who has this private key. And there are different kinds of variants how do you do this, but leading standard, there are different kind of centralized standards coming from IT companies. For example, in Latvia, we use eParaksts.lv infrastructure, which is solution developed by Microsoft. Actually, Latvia was used as a testing bed for their solution, and that's one of reasons why we got this electronic signature solution much quicker than other countries. So Latvia was small enough to not break everything, but big enough just to test how it works. But for decentralized solution, implementations are based on standard called Pretty Good Privacy, or PGP, but this is standard. Initially it was developed by Symantec company, but later it was published as an open internet standard and was called OpenPGP. And this standard is implemented in utility called GNU Privacy Guard, where GNU, of course, is this abbreviation coming from operating system developed by Richard Stallman, which today is usually used as a GNU tools and GNU utilities. For example, in Linux-based operating systems, we use Linux as a kernel, but we use almost all utilities coming from this GNU operating system. And so it was also pun on this PGP standard because GNU Privacy Guard is abbreviated as a GPG. So these letters are swapped here. So remember, if you use open standards, you shouldn't say that you are using Pretty Good Privacy, because this was initially a proprietary standard developed by Symantec. OpenPGP is actually internet standard, RFC, blah blah blah. But usually what you use, you're using GNU Privacy Guard utilities or GPG to use this standard. How does it look for users? I will later show you for practical exercise how you get everything working. Not everything, but what you need to get working. But you can use PGP standard or GPG utilities, for example, to sign, to encrypt emails. For example, when I check for OpenGPG key managers, I see that I have my set of keys here. And and this is key. I think it uses RSA algorithm or cipher, and it has this private key and public key. So depending how you use it, it is used either for signing or encryption. And if I write some message here, and send it to myself, I receive message which is in just plain text. And if we look how does it look on the server, and we see how it actually looks when we look into details of bits. So here, similarly to web, it has quite a lot of so-called headers, which is key, column, value, key, column, value. And here it is plain text. Here is content, and somewhere here it should be also subject. If I write another one and want to sign it, Then I can sign it using OpenPGP. Do not encrypt, just sign it. Let's double check. No encryption, but it is signed. Then here I see that this message is signed. Signer key ID is such one. I can check on more details. And what is happening on server is that it is actually encrypted. Only subject is seen here, but what we see here is that key data blah 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 and public key. So what is happening here in when you sign something? When you sign something, you encrypt it with your private key, and private key of course belongs only to you or any person who personificates it to you. And then actual data are sent here as a ciphertext, but anybody can decrypt here, because here these data are sent together with my public key. And if I trust this public key, so I use this public key to decrypt this ciphertext, and you see here that this block IS encryption is also used. So even though message is very short, when it was encrypted, minimum amount of data I needed to send is following, because there is no shorter block to be used for this encryption. And when I decrypt this ciphertext with this public key, I get this signed message back, and that means if I could decrypt it with this public key, that means it was encrypted with this private key, that means this message actually came from me. Other thing what you can do is to write encrypted message and then I use it to require encryption, and I will not sign it. And here you can also say attach my public key, but I will not do it, and I send it. And here it says that this is encrypted message. And how encryption works? Encryption works similarly but completely differently. So now here are metadata, but only thing I have here is the key PGP message. Why? Because I didn't include my public key, because when I send encrypted message to somebody, what I'm doing, I encrypt my plain text with public key of receiver or recipient, and then only recipient can decrypt it using his or her private key. So encryption means that I need to get a public key of my recipient, and of course if I send it to myself, I have public key of myself. So and then I encrypt it with a public key, and to decrypt it, recipient needs to use his or her private key to decrypt it, and everybody else just say this abracadabra here. And then of course I can do both. I can encrypt and sign. So I say require encryption, I say digitally sign this message, and I may say also, and then public key of course is attached, and I send it. And now here my email client says that it is both signed and encrypted. And what does it mean? It means following, that first this message was signed. What means signing it? This means I get the hash out of it, and then I encrypt it using my private key. And then anybody who knows my public key can decrypt it and see that got the same result. And if I also encrypt it to my recipient, then of course after that I encrypt it again using public key of recipient, and then this recipient can decrypt it using his or her private key. And you see here that when you use encryption inside encryption, amount of data becomes larger and larger because of these limits of these block ciphers, how short this message can actually be. And hopefully it is not too confusing to you, because I am sending message to myself. But if several persons would be involved, then for signed message this person should know my public key to check that applying this public key he or she gets the same message back. For encryption I need public key to recipient, and of course recipient uses his private key. And for signing an encryption I use my private key to sign, recipient uses my public key to check it, and I use public key of recipient to encrypt, and recipient uses his or her private key to decrypt it. So that's about this demonstration. Okay, now just to resume before break. So let's say here is Valdis and here is Pēteris, and we have both private key and we have both public keys. First we need to exchange public keys, so that means I also need private key of Pēteris, public key of Pēteris, and he also needs public key of Valdis. So on you may have very long list of these public keys here. And when I sign something, so here would be sign, what I use my private key to encrypt, and so it becomes something like encrypted with private key, and this signature here is inside it. So I send it to the Pēteris, and Pēteris uses different key to decrypt it. So it applies my public key to decrypt and get its message back of signature. So that is about signature. If you want to encrypt, you apply it differently. So you have encryption, text for encryption, and I apply key, public key of Pēteris, not myself, to encrypt it. And I send it to Pēteris, so he receives it encrypted using public key, and here is this encrypted message, and then he applies his own private key to decrypt. and gets this encrypted message back. And you see, always you use private key, then public key, or public key, then private key to decrypt them. And depending on what you use to encrypt and what you use to decrypt, you can use it either as your digital signature or to encrypt it for recipient. And you see that these private keys are never swapped with somebody else. It is used only locally, only for Valdis or locally for Pēteris. I hope that this made it a little bit more clear. Any short questions which I can answer shortly about that? So, we are continuing about security and encryption in this case. So, when you have this public-private key encryption, one of important aspects is how you distribute your public keys. And problem in general is called key distribution and agreement. And what can you do? First, you can do different kind of public announcements. There may be different ways how do you do this. I will show you one case particularly for email. Then there may be different kind of publicly available directories like databases where you put your public keys. And both of them have their problems, so not everything is ideal. But in general, what is happening is that for well-established approaches, for standardized approaches, there are organizations called certificate authorities. Certificate authorities provides you service, usually for free for these who use as users, for some fair amount of money for these who want to publish their certificates, and then they provide this service where you can check what this public key for which particular user belongs. So what do? You create your public and private key pair, and you submit your public key as a key request to these certificate authorities. And then they may do some additional checks. For example, they check that you respond to a particular email, what you have claimed here, and other things. And then they sign with their own private key your public key with your metadata, and then you get this information here. You can check signature of this certificate authority, and that means that this particular certificate authority signed and checked it that this particular public key belongs to this particular user. And mainly used standard to exchange certificates is protocol called X.509. So what it standardizes? It standardizes how do you issue certificate confirmation requests, how do you issue certificate revocation requests to these certificate authorities, and how these authorities sign and publish these keys. And the best well-known established standard for it is certificates to use HTTPS protocol. For example, if I open website odo.lv, it uses HTTPS protocol, What does it mean? It means that the interaction between client and server is encrypted. And how can you encrypt it? Using unknown, probably harsh environment in between. You use public key exchange. Client connects to the server and server sends back its public key. Then client creates a random number called nonce. Let's say 1, 2, 3 or whatever, and encrypts it with public key. So this 1, 2, 3 is, let's say, public, I used it as an end, is encrypted with public key and sent back to the server. And only one who can get this 1, 2, 3 back is server, who also has private key. So it applies to this received data its private key for decryption and gets out one, two, three, and then all these data are encrypted using some established cipher, usually AES, with chained blocks. So you have blah 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 blah, and everything is encrypted with 1, 2, 3 and sent to the client. And here we see blah 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 blah, which is encrypted with this key 1, 2, 3. And then this client applies this nonce 1, 2, 3 to decrypt it and got some data back, and then sends some blah 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 encrypted with 1, 2, 3 back to the server, and so then everything works in such a way. Why they use this random number generated here? For performance reasons, because applying, especially if you use RSA keys, then applying private and public key encryption is very slow, 1,000 times slower than applying symmetric key with just using XOR operations, where X means exclusive OR. And because of that, so here this thing is happening slow, applying public key to encrypt 1, 2, 3, and applying private key to get 1, 2, 3 out of this cipher here, encrypted with public key, but everything else is using this symmetric key, which is much faster. And there have been some of security issues that this nonce actually is not a very good random number. It has some determinant properties inside it, so if this conversation is long enough, somebody can actually guess what this random number was. But as far as I know currently, all these leading browsers like Firefox, Chromium do not have such security issues, at least no security issues anymore. And problem here is about man-in-the-middle attack. What is if this public key, which was sent from server, actually was from man-in-the-middle? How can you ensure? So you ensure that this public key is registered into certificate authority. So what you got here is involved party, that with this public key you also get digital signature from this certificate authority that they confirm that this public key belongs to this server, odo.lv in this case, and this is proper public key. And of course they have signed it with their private key, and they also show their public key to you, so you decrypt this signature with public key and check that you get the same hash sum back. From user perspective, it looks like following: that if you use HTTPS protocol, you see that this connection is secured And here you can check details about these so-called certificate. So certificate is your public key together with metadata for authentication. So somewhere here is public key itself, and you see it uses RSA algorithm with 2048 bits in length, which is not the biggest one, also not the smallest one. But here it also says that this public key belongs to website odo.lv, that this public key was registered in DigitCert and it is valid from this date till to that date. It also belongs to website www.odo.lv, and somewhere here are the signatures coming from DigitCert itself, and my browser knows that particularly DigitCert is one of these known established certificate authorities. They make like 3 structure. There are some few very prominent ones, and then if you show that your security is good enough and you pass security audits, you can always be like a subcontractor for these companies and issue your own certificates. And here, of course, there is their public key info, which you need to use, for example, to decrypt back this signature to know that this particular public key belongs to website odo.lv. And so what web server administrators does, they create these private and public key pairs, and they submit these public keys as certificate requests to these certificate authorities, and then they check. In most of cases, they just check that you respond to this particular domain using email and other things, and that's it. There are also some services like for free, like let'sencrypt.org and some other things. So, now about software vulnerabilities, which is another thing how you can break into it. So as I told you already, software is complicated. Nobody knows everything about used software and hardware. Everybody barely knows what he or she needs to do his specific job, and therefore there are different kind of problems. And one of problems how you can break into system is first you have system connected to the internet, and this means that everybody who is also connected to the internet can be trying to break into your system. And one of still common problem how they can break into the system is to put different kind of inputs, wrong inputs into your system, and to start programming it with some kind of input. How does it work? It works in the following way, that when you need to read some input from your system, you need to reserve memory inside computer to store this data. And especially if this reservation is done manually, like in C, C++ programming languages, you need to say that here is my buffer, for example, for username, and here is buffer for password. And in most of cases, for example, this buffer is 1 kilobyte in length and kilobyte here. You know that username is just few characters, everything will be fine. But if you do not do proper check for input, what may happen is that this user actually may provide username which is much longer than 1 kilobyte. And if you do not have guard here, that this input cannot be written in longer data than here where this buffer ends, it writes something here in this computer memory which was actually used for something else. And if here there is some memory which was used for instructions to run actually computer, then with this invalid input, these instructions may be changed and this program starts behaving completely different. As I told you, today most of programs use these guards that nobody can write in this part of memory which is shown just which is used to store instructions for this computer, but these guards are also not 100% secure, so it may still happen. So in general what happens is that in reserved place in memory somebody can put more data than it is needed, and sometimes you are allowed to delete some data and then you can delete a little bit more than you are allowed, and then you can put some data into this part of memory which belongs to something else. And here we may go back to this simple assembler computer online. And what is important here, you are not required to understand assembler programming language, but what is important here is that this program counts steps and it runs into loop for required amount of step here and then it stops. And when you convert this assembly language into executable codes for this particular computer, so here is this random access memory for it, which is used to store data. And somewhere here you should see 5. 5 in hexadecimal is the same 5 as in decimal, I think here. And here are numbers which represents instructions to move data, to increment counter, to increment other counter, write some data and stop. So it writes some values. I think it could be either somewhere here. Let's run it step by step. What is important here is instruction pointer. Instruction pointer shows in which particular cell of memory this number will be used as a code for execution or instruction for computer. And of course it goes one forward here and its value shows which particular instruction should be executed next. So, and it goes 5 times and it stops. But if somebody makes mistake and says that steps should be 6 here, then here is not enough reserved memory. And if we run it, first I need to assemble it and then run it. What is happening is that now it rewrote one of these codes here, which was actually writing its value 06. You see it write from here 01, 02, 4, 5, 6, 7. And now it walks into infinite loop because this cell of memory was actually reserved to store instruction for some of this code, but now it got a different value. And if we rewrite a little bit more, so now it will rewrite these empty spaces somewhere till to here. And again, it went into this part of memory where its instructions were used. And we can make it much faster. And again, it went into infinite loop. If we rewrite something more, behavior, sooner or later it will crash, because it will not be able to execute one particular of these instructions. Okay, let's make it very long here. And so this is one problem, how you can pass some wrong data into computer, and with this data you can actually change its behavior. In more complicated situations, there is another example. We can use C programming language, which is, you can use it improperly. And what is important here? That we need to enter password, and if entered string is passed, then it says that it is correct password, and then it executes this part. So, for example, it gives you root privilege to do something else. And when you compile it, and here I need to compile it with some old school approach, for example, no stack protector. So that means if I would compile it properly, then I would get crash when I input more data. But if I compile it improperly, so it says wrong password, correct password, root privileges are given to the user. Okay, but if I write something much longer, it wrote wrong password, but also root privileges given to the user. Why? Because this particular check here didn't work correctly, and this value was overwritten with something else, which was considered true, and so I still got root privileges even though I entered wrong password. And of course, if I recompile it safely, and then try to rewrite it, I get stack smashing detected. So in this particular case, there are different kind of types of memory. Stack is one of subtypes of memory. So it saw that this part of, some part of this actually would overwrite part of memory which is marked for execution, and it just said that my program crashed because it tried to write something into a restricted area. So, and because of that, you need to do different kind of input validations. You need to check using automated tools or more properly how you manage your memory, because otherwise any program which takes some input may be reprogrammed if you do not carefully check amount of data given to your application. And all these computer malwares are mostly using such kind of vulnerabilities. If there is some running program and it takes some kind of input, and almost any program needs some kind of input and produce some output. Otherwise, question is what this application or program actually does. So they check for different kind of weaknesses. One of other weaknesses is concurrent problems, that if some program does something executed in parallel, there may be different kind of race conditions, and then they may be different kind of problems, and they reuse that. But these are more details. But in general, problem is that we are using this one name and architecture for our computers, because this is very good from universality perspective. We can load any data, this means any program, and execute it. So we can load and execute different kind of programs. But because of that, if we are not careful and we do not restrict writing in places of data where are called our instructions for this program, then any program which takes input may be reprogrammed to something else. And so these different kind of malwares are always scanning for vulnerabilities. They check does somebody responds to this particular IP address, try to connect to different kind of systems, and then they try to check what kind of vulnerabilities these systems have. And then there are different kind of types, like Trojan horses, systems which actually you invite in system by yourself. So proper malware are like virus which spreads by itself, because if these data are provided to your computer changes its behavior and also spreads this virus similarly to real life to other computers. But some of viruses are not so smart. For example, Trojan horse are malicious software which you have to run by yourself. And how can you be so dumb? Very easily. You search for some kind of freeware, for some freeware utility, for your microphone recorder, for your some kind of editor, painter, whatever, etc. So it looks like this is editor to edit some kind of data and to do something, but it also steals some data from your computer or your mobile device and sends these data to some big browser or to something else. So worms are these viruses which are using network to replicate themselves, so they run independently using global network. And then these hijacked and cracked computers may be used as a zombies to use this as a legion of computers for your malicious needs. And how can you use them? You can use these hijacked computers to dig bitcoins, or to hijack other computers, or to make inconveniences for some companies, etc. One way of Trojan horses is, for example, I have received calls that somebody says there is some problem with my computer. Can I install myself as a team viewer or something like this on my computer, and they will help me to solve this particular problem. So this is actually Trojan horse which uses actual human as a weakest place in this chain between computers, that you actually accept this and do everything by yourself. And usually they say there is some problem with my internet bank account or whatever. And so when they have these hijacked computers where they gained control, either using this Trojan horse approach when you install something by yourself, or actually it has some weakness against some computer worms and viruses, then they can run something else on your computers as well. One of the things is, for example, they can attack somebody else using different kind of denial of service attacks. So if they have a bunch of computers like zombies, they can focus these zombies to do something bad for Facebook or Microsoft or Apple or whatever. And so if there are many of these zombies connecting to Microsoft or Facebook, then of course they have big problems because valid users cannot connect to them because they are busy dealing with these requests coming from zombies. Then there are different kind of spyware which steals your private data and puts to Big Brother. Actually, like Facebook is spyware which you invite to your home like a Trojan horse. But of course there may be spyware hiding as different kind of small utilities for your computer, for your mobile devices, etc. Particularly about Trojan horses or Trojan and spyware, very important part is centralized package management, because particularly for Microsoft Windows, their approach, at least until recently, was that mostly they were used as a platform for other closed source applications, and Microsoft is not legally allowed to make copies of these other closed source applications. So that means Microsoft by itself could manage package management only for Microsoft Windows, Microsoft Office and similarly related applications, and everything else should be downloaded, installed using approach. You open someplace in internet, download it, execute it, assuming that this is proper tool. But of course, with such approach you can install malware quite easily. But for open source based systems like Linux based system, this is much less problem, because in 99% everything you need you install using standard package manager, and then this means you download it from proper place, signatures are checked, you know that this is not malware, this is not Trojan horse which you are installing. When you install GIMP editor, you actually install GIMP editor, not GIMP editor, together with something else, which actually has happened with GIMP a few years ago. And then there are different kind of scareware, etc. So all these applications work in a such way that they break into your computer, then take control over it, and then they can do different kind of things. So what can you do about this? First is that one thing is you use so-called air gap between your very secure computer and internet. So that means that, for example, if you need to hold some very private keys, like you have Bitcoin wallet and you own millions of dollars in that Bitcoin wallet, then probably you shouldn't store these keys to access Bitcoins in network connected computer. So you store it on some computer which has never connected to the network, and if it's never connected to the network, then you will never have any problem with all these malware coming to your computer through the network. What else you can do? There are different kind of vulnerabilities inside network. For example, in local area network, which we talked earlier, you use actually Ethernet in most of cases to exchange Ethernet frames between computers inside the same Ethernet network segment. And absolutely similarly it is also for Wi-Fi and Bluetooth and USB. But then you need to establish link between actually logical IP address for IP protocol and a Ethernet MAC address for actual device connected to the network. And if you hijack these ARP requests from address resolution protocol requests and you ask, for example, what MAC address is for this IP address, and some hijacked ARP server, which is usually DHCP server, which auto-configures your internet protocol for your computer, is hijacked and says that this MAC address is something completely different, then you can get completely wrong answer about which physical computer you need to connect to with this particular IP address. How do you avoid these problems? Example, in most of cases, that is one of reasons why you should use passwords for your Wi-Fi network. Otherwise, if somebody connects and also provides ARP service to your Wi-Fi network, again, you may connect to a completely different computer as you were intended to connect to. So that's about local area network. In global area network, again, you can hijack some gateways or routers between your computer and remote computer. Because, as I told you earlier, there are many routers in between your computer and your target computer, and all these network packets are replicated and resent mostly as new Ethernet frames from one computer to another, from one computer to another until you reach the end. But if something here is broken, and some of these internet service providers actually reroute your packets to some completely different place, then again, you will not connect to Apple, Microsoft, or Facebook or Google. You will connect to some completely different company with their malicious server. How do you deal with this? There are different kind of things, but most reliable thing is, again, that usually all these owners of routers know what is normal traffic, and if some router says please send this particular packet with this target address to that direction, they usually drop this packet because in most of cases it looks wrong path. Of course, nothing is ideal because sometimes actually some of these routers may be down and it should be rerouted. So, and because of that, this is actually moving target, so it's actually arms race between these who own routers and manage them and these malicious things. Then, of course, somebody may sniff these packets or data. For example, if it's not encrypted, then everybody who is between you and your target computer may read your data transmission as open book. And that's one of the reasons why Google, for example, downvotes all web servers which do not use encrypted HTTPS protocol anymore. And if you don't check public key certificates, and this is actually done by your browser automatically here, then there still may be man-in-the-middle attack, because anybody can sniff packets in following way. That here is you, and here is server, and of course you use HTTPS. This means it's encrypted, but man-in-the-middle does following, that it says that it is server for you and it is client for the server, and it still uses HTTPS protocol here. So everything is encrypted here, everything is encrypted here, but here for this man in the middle it is encrypted, all these data are read and then resent in a encrypted way to you, from you back to the server and again. So how can you avoid these things? You use these certificate authorities, because encryption can be done with private and public key. For Odo.lv, only this one set of public and private keys. So if somebody says that he is also Odo.lv, he will not be able, at least if everything works correctly, to register another set of private and public keys belonging to the website odo.lv. And if you see something like this, can I show it to you? Oh, I think I can show it to you. So, it looks something like this. My web server allows to connect to it using just IP address, not its name. But then we have a problem, because this public key is registered for website with name odo.lv, not with this IP address. And that would be something like man in the middle. So, I can accept it. Not here. It doesn't show any content here, unfortunately, but if it would say that I can use HTTPS protocol for this IP address, then I would get this particular content. And here I see that even though it is encrypted incorrectly, because this public certificate do not belong to this IP address. This public certificate belongs to a website with name odo.lv. So encryption doesn't show that everything is secure. Encryption with properly registered certificates is secure. Then you can also hijack something like established connection, and you continue some TCP/IP connection. Other things, DNS security, it is you can call what IP address is for odo.lv, but some of malicious servers may say that IP address for odo.lv is not this one, but IP address is something completely different. And then particularly for web servers, there is problem with JavaScript. JavaScript is very powerful programming language which does very many different things on your browser. So when your browser downloads JavaScript, it downloads instructions to execute. And if you download malicious instructions to execute, then of course your browser executes malicious instructions. And what can you do about this? First, you need to check that, for example, if you allow some kind of input, like my website allows to write comments, even for unauthenticated users. Let's open this place. Okay, I can show you to use it. So, you need to resolve some CAPTCHA, which means completely automated procedure to tell computers and humans apart. And then, of course, it do not, for example, to put here JavaScript code which will be executed, because if it would be allowed, and here let's say pseudocode, if here there would be instructions that no, browser needs to open some completely different website, then of course my browser would do this. So that's one thing. Other thing is that, for example, when you do different kind of web portals, you actually allow to put some more content from other websites inside your website as a injected content, mostly for advertisements. But again, for these advertisements there may be malicious Java code which again tells to do malicious instructions to computer. And what can you do about this? First, you do different kind of things. You, for example, do not allow to put JavaScript code into this injected content. Other thing is that, for example, if you open like delphi.lv and somewhere here there is instructions for JavaScript coming from different website, not for delphi.lv but from ragiunnagi.com or whatever, then because this is my website, my browser just refuse to execute this JavaScript code. So it is called the same origin or the same source. So if I open this particular website, only these JavaScripts will be executed which are downloaded from this particular website, nothing else. And we can check. And you see here that not all JavaScript is actually downloaded from delphi.lv. There are some other websites as well, and in this particular case delphi.lv says in some headers here that these particular scripts are actually allowed to be run, and I either accept about this in my computer or do not accept. Single origin principle it's called. So problems with single origin principle is that it is a little bit harder for different kind of integrations, etc. And what is actually happening is that if you go into details how HTTP works, so this website should be declaring which particular scripts are allowed to execute these different places. So how does it work? When you open this particular website, you are thinking that you are talking only to one particular web server with network address delphi.lv, but it's not true, because with all this additional JavaScript code, with additional dynamic HTML code, it does much more. And there is a Firefox plugin called Lightbeam, Saturday date white still. Okay, and this plugin actually tells to how many other websites my browser is actually connecting besides this initial server delphi.lv by executing these other instructions which this server provides to me. And you see that here is in center delphi.lv, then there is Facebook, piano, blah blah blah. You think, okay, it's not so bad. But what is happening here is that I have installed also blocker for advertisements, uBlock origin, where u actually is micro. So if I switch it off, what would be for standard web browsers? So I do not try to filter anything out from these advertisements and refresh this page. And then now my browser accepts everything, every instruction sent from Delphi.lv web server. First, it takes much more time because much more data are sent, and that's how exactly it looks like. I opened only one single Delphi.lv, and I also send some data to all these other websites. And it still continues because it still works in background to connect to some other websites as well. And that's how much you should know about your privacy when you are opening some websites without ad blockers and without private browsing. And if I open Taiwanet, so here is Taiwanet with ad block switched on. So that's about these things. And if you care about your privacy, so one of the stupid things is, for example, to use Google search and to search about some health issues, etc. Because, for example, if I open Google, usually I'm authenticated user already connected to it for YouTube and other things. And if I search about some private things here, of course Google remembers these things and knows about me. So instead of that, you should use first like DuckDuckGo, and second you probably should use private browsing mode, where also your browser do not remember anything. So you open this, and if you need to care very seriously about these things, there's also a browser called Tor browser. And what Tor browser does, Tor browser connects to so-called onion routers. So Tor is abbreviation from, what is T? I don't remember, but OR are onion routers. So when I open some website, so here is log file in real time about my Apache web server, and I open website odo.lv. What is happening is that first this browser creates some randomly created connections to these onion routers. So while it's thinking, I will illustrate to you. So this is entire internet. Somewhere here is odo.lv, and you connect to the internet with your computer. So usually you go through well-established paths through these routers to odo.lv, and because you use network address translation, somewhere here will be your public IP, how you connected to the internet. But then there are these onion routers which creates randomly created connections, and then they connect to this final state, and my web server sees only this last router to send this data. Because of that, it is much slower. And for example, now I see I should actually I can open, for example, and so probably this is this IP address from which I connected to this web server. But if I say create new circuit for this site, then it will create another, and you see that now this IP address is completely different. So then even if you use Google, then I will not be surprised if Google will refuse to work through this Tor network. Yeah, it opens, but it says you can't continue, because in this case Google do not know who you are, and if they do not know who you are, it's not very interesting for them to provide any service. Because remember, Google is not in search business, Google is in advertisement business. I think I will not get through this. I think it will just do this forever and it will not work. But if you open, for example, then you can still search it. So now I'm looking on chat. So I do not know what is Darknet browser. It's something new to you, but particularly for Tor browser, if you use Linux-based operating systems, then you install it using a standard package manager, like this for Ubuntu-based systems. And then these packages which are downloaded from these remote repositories are checked for checksums and signatures and installed, and then you just run it. But for other things, of course, other operating systems, it is different. So now let's drink something. Now about your practical exercise. Your homework will be more narrow than I explained it to you for now. You will need to prove your skills and knowledge a little bit about signatures and encryption using this PGP standard, and particularly using GPG implementation of it. And to make my life easier to check your knowledge here, you will be able to do your integration with your mail reader, and I will not be surprised if most of you use Gmail. Then you just say, for example, So because I do not know what kind of term should be searched, because protocol which should be used is OpenPGP, or PGP in short, and GPG is just one of tools of sets which uses this protocol and implements it as a set of command line utilities. So, example, to use this PGP in Gmail, you search for it and do yourself. I do not use Gmail directly. All Gmail emails are sent to my local email, but because of that, so we can't do good integration, and therefore you are required to work with simple files and simple basic utilities, because PGP protocol is a basic foundation of these features, and then you can use different kind of tools and utilities which actually use it. And in this exercise my recommendation is to use GPG. And how do you install it in Linux? In Linux you just say in command line, I think it's easier, sudo apt-get install GNU PG, but I think it is installed in this virtual machine. And then you need to do configuration. Of course, first thing to start using this, you need to generate public and private key pair for it. So in command line you call GPG parameter --gen-key. Let's say and that is okay. And here it has integration with so-called keychain. I will not use it, so here I will say no, yes, protection is not needed. Okay, yes, protection is not needed. So what does it mean? It means that I will direct access to my private keys here. For example, this private key. It is not password protected, but because I think my virtual computer is secure enough, I will deal with this. Then, for encryption, of course you need to provide this public key to everybody else. And you can send this binary key, which is now it's stored in database somewhere here. Fabring KBX. So here in this database file you may have more than one public keys. Therefore you use export, and you export it as a plain ASCII file with base 64 encoding. And your email was .lv. And so here is this public key, extracted from probably many public keys if you have more than one. And then we need to create plain text, for example, and what should be content there. Okay. And then you have to do two different things as far as I remember. First, we need to sign it. And to sign it, this means we encrypt it with private key. We need to provide public key to it for checking purposes. And if I use these numbers, so here of course you need to write your actual numbers here. What you do, you sign this particular document, output of signature will be this document, and because here I am not showing which particular key to use, because I have only one key, of course this default key will be used to sign it. And here is this signed document. We see here that here is somewhere actual content, what is file inside it, and what is its content, and every other data here are binary data about this signature. And then, if we are curious, we can check it as well. Verify. Something is wrong. And down. Then everything is built in, I think, in such way. So if signature is part of actual content, we just say verify, and it says that good signature, blah blah blah. And then we need to encrypt it, but we need to encrypt it not for ourselves, but for receiver, in this case Valdis Vitoļņš. And here is another way how you distribute public keys. One of the things I showed you was key distribution from user's perspective, not from web's administration perspective for these certificates, but particularly for PGP keys. There are different kind of websites. Where you can register your public key, and as only authentications I use is your actual email address, what you have put here in description field of your key pair. And in one particular case I have registered this public key in website keys.openpgp.org, and if you search for this email, so you get reference to this public key and you download it. I think I saved it in the downloads folder. Actually I have more than one. So I would have something like this one. But you could rename it as you like. And then to use it you have to import it in your database of GPG. And here I didn't follow instructions carefully. I didn't say save it as this name. So I have to say GPG import this strange name here. And if you are curious, I see that now I have two different keys. My own, in this case I'm impersonating Jānis Vitoļņš, and here is this imported public key, Valdis Vitoļņš. And if I look on secret keys, of course I have secret key only for myself, this user. And now when I have imported this target public key, I can encrypt it by using public key of this target recipient. I think I don't need to change anything here. Yes, I want to use this key. I want to overwrite it. And I created such file. So, what are deliveries? Deliveries are this file. This file and this file. So, and if I want to still actually use my code, so actual signature should be on this. That is signature. Sign it, not signature. This is my signature public key. And this one, encrypted one. I don't need this anymore. And I don't need this. So something like this. GPG is encrypted file. This is my signature and this is public key. So here problem is that all these files are binary files. And you may mess up something with names here, and then I will not be able to decrypt it. And then you upload it. I think that is easy to do. I will show, for example, how let's make so I will get these files from you on my computer. So now I'm not inside virtual machine, I'm inside my machine. I need to import. There is instructions. Instructions are inside virtual machine. here I see a problem. How I will now, I think I can do, say, in solving way as well. Yeah. So I imported public key of this particular user, and then I can GPG check. Verify. This is the signed document. And I see good signature from blah 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 blah. This key is not certified with a trusted signature, so that's okay, because this particular key is, for example, not registered in some of these public certificate authorities. And to decrypt, I think everything should be working more or less automatically. And yeah, so if I can find these keys, so I have is it proper file? I don't remember what I wrote there. I'm not sure. I think I should see Jānis Vītoliņš there, but I already deleted temporary files, saying to you that it's not necessary. So here many things may go wrong, because you may mess up these extensions of files, etc. But this is only way how we can prove that we in general know how signatures and encryption decryption works using basic tools, not some other tools built on top of these utilities. So, any questions or comments on that?